class number 5 for college geometry. Welcome one, welcome all. Hopefully, can everybody hear me okay? Just making sure. You may notice a slightly different look and feel to the program. Adobe Connect came out with a new little update, so I'm just making sure everything seems to be working, and everything does seem to be working, although we only have 4 students in here for now, but hopefully we'll draw a few as we move along. But be that as it may, it is time for college geometry, and it is time for class number 5, and today we are going to be discussing proofs and geometric proofs. Before we even discuss geometric proofs, I want to discuss a few logical rules, and the reason why we're going to discuss logical rules is because really those are necessary in order to prove something. Whenever you want to prove something, you have to establish it using rules of mathematics, but also rules of logic. A proof uses logical reasoning, which infers one fact from another fact. There's deductive reasoning that draws a conclusion from a series of statements. A series of general statements can be used to glean one particular specific statement that logically follows from the rest of them. Conditional statements, if, for example, we know something is true if a condition is met, and we know that the condition is met, so therefore we know that the statement is true. And a proof can even be indirect. For example, if you want to prove that something is not a parallelogram, well, it's very difficult to prove that it's very difficult to prove a negative in general. Well, what you'd really have to do is say, if it would be a parallelogram, then opposite sides would be equal. In this case, opposite sides are not equal, therefore it is not a parallelogram. That's an indirect proof. An indirect proof is when you are making an assumption based on what would apply if a certain factor existed, and then showing that those factors do not exist, and because of that, you make a deduction that whatever your original proposition was in fact not the case. Okay, that's generally speaking what a proof is. In order to start, before kind of as our little bit of background to proof, I remember when I was taking geometry, we actually spent quite a bit of time on logic. Now, we're not going to spend that much time on logic. That's not really an essential component of this course, but there are a few important rules that you need to know, that you need to understand for purposes of proofs and for purposes of logical reasoning. And by the way, this is very important for law as well. You know, most of you obviously are studying to be paralegals or eventually maybe even to be lawyers. And these logical rules, not only are you going to see them on a day-to-day basis in law practice and analysis of cases, if anybody here ever decides to take the law school admissions test, there is an entire section on the law school admissions test called logical reasoning. It's actually half the test, not including the essay part. Really, there are 5 parts on the essays. There's an essay there on the LSAT. There's an essay part. There is 2 logical reasoning sections, one reading passage section and one kind of analytical reasoning section. And in the logical reasoning section, and even the analytical reasoning section, knowing these logical rules is a must. Now, we're not going to go through every single logical rule, but we are going to go through some of the basic ones. Really, only 3 basic rules that I want to go over. And really only 2 of them. And they're all pretty obvious, but they're the sorts of things that it still makes sense to discuss a little bit. Let's take the following statement. You see up here on the slide, if it's raining, then I carry my umbrella. That is a classic conditional statement. There's an if-then. If I tell you that P represents it's raining and Q represents I carry my umbrella, then I can write this statement, if it's raining, then I carry my umbrella, as P then Q. That arrow is a conditional. There's also a few other symbols, by the way. I'm not going to go into them too much, but this symbol means and, this symbol means or, and this symbol means biconditional, and means essentially they're both true, or means one is true or the other is true. Biconditional means if it's true if and only if the other statement is true. I don't want to worry about those for the time being. The only one we're going to worry about today is the conditional. The rule of detachment, and this is really the most obvious rule you're ever going to see. If P then Q is true, well then let's say we prove that P is true. Can you deduce anything from that? This 3 dots over here tells you what it proves. Well then, by definition, you can prove then Q is true. Because if we know that if P then is true, then Q is true, and we know that P is true, then by definition Q is true. So for example, in my statement, if it's raining, then I carry my umbrella. If I tell you that it's raining, can we then deduce that I carry my umbrella? Yeah, common sense. That is the rule of detachment, also sometimes called the rule of modus ponens, but you don't have to worry about that. Then there's another rule. And really, the next two rules that I'm going to discuss, the modus tollens rule and the contrapositive rule, are really the same rule. And that is, I want to discuss a couple of things. Number one, a statement does not, I'm not even going to write it over here because it's written on the slide. I was going to say a statement does not imply its own inverse. Inverse is the opposite direction. So for example, if P then Q is true, that prove that Q then P is true? The answer is not necessarily true. For example, back to my statement, if it's raining then I carry my umbrella. Does it have to be true by definition that if I carry my umbrella it must be raining? Based on the P then Q statement, based on the fact that if it's raining I carry my umbrella. So does that imply that if I carry my umbrella, then it's raining? The answer, as Devore says, is no. Why? Well, from a logical perspective, just from my example's perspective, I could be carrying it for a different reason. I could be carrying to keep out the sun, or I could be carrying to keep out the snow, or the hail, or the sleet, or whatever. The fact that I carry my umbrella does not necessarily mean that it's raining. A statement also does not imply inverse. Inverse means, in case not P, then not Q. For example, if it's not raining, then I don't carry my umbrella. Is that necessarily true? Also, that's not necessarily true. Just because it's not raining, I might be carrying my umbrella for another reason. I might be carrying my umbrella because it's a good walking stick, or I might be carrying my umbrella to keep out the snow, or to keep out the sun, or whatever it is. So a statement does not imply its inverse. A statement does not imply its converse. This is the sort of thing, by the way, that, when you look at people, just regular people making arguments, this is a very, very significant mistake that people make. Just because I tell you that if one thing is true, something else is true, that doesn't necessarily mean that if the first thing is false, the second thing is also false. A statement, however, does imply its contrapositive. Contrapositive is the combination of the inverse and the converse. That is the contrapositive. Not Q, then not P. Let's write it down. Let's write down the contrapositive of my first statement down here. The contrapositive of my statement is, if I do not carry my umbrella, then it is not raining. Is that statement true? Assuming that first statement up there is true, if it's raining, then I carry my umbrella, is it also true if I do not carry my umbrella, then it's not raining? The answer to that is yes. It has to be true by definition. Because if it's true that if I'm raining, then I carry my umbrella, well, if I don't have my umbrella, then it cannot be raining by definition. So a statement does not imply its inverse, which are both nots. It does not imply its converse, which just flips it around. It does, however, imply its contrapositive. It does, however, imply that if the second element, if the thing that upon which the statement is conditional on is not true, then the original statement must also not be true. Okay, those are some general, basic logical rules. And with that in mind, let's go through a couple of, and I'm just going to go through the slides over here, and then we're going to look at a bunch of examples. That's really what we're going to cover. I'm not going to spend a lot of time on the slides. I'm going to just show you the slides in terms of what geometric proofs are and what their structures are, and then we're going to go straight to a bunch of examples. Thank you. Okay. Conducting a geometric proof, or a logic proof for that matter, although we're not going to discuss logic proofs, is that you need to establish a statement of two columns of statements or reasons. The reason why something could be true is either because it was given to you as part of the question, or because it is an established mathematical rule, or because it can be deduced from an established mathematical rule, or a rule of logic, for example, like the converse, the contrapositive, or the detachment rule, the ones that we just discussed. If you can establish, using what you've been given and using the deductions from what you've been given, well, then you can prove something to be true. And this is the basic structure of a proof chart. You'd have statements and you'd have reasons. Usually you'll have to be given certain information to start, so your first statement or two is going to be based on the fact that it is given. And at the very end, your last statement will be hopefully whatever it is that you're trying to prove. Okay, let's take a look at this example over here, and we are going to prove this together. All right, 1 second. Okay, I am going to make a little chart over here, and we're going to prove together what the okay, this is, again, I'm not all right. Believe me, it's not that easy to write with these pads, with these writing tablets over here. Okay, anyway, we're going to say statements, and then we'll put a reasons column over here. And we've got, let's look at the one on the slide. It's given that AFDE is a rectangle, and it's also given that DCE is equal to the measure angle of FBA, and so prove that ABCD is a parallelogram. So let's quickly write on the diagram what we've established. AFDE, that's the big thing, is the rectangle. What does a rectangle mean? Well, first of all, it means that opposite sides are equal. So this whole thing is, so AF is equal to DE. It also tells you that ACE, in other words, this whole side, is equal to this whole side. What else does it tell you? What does it tell you about the angles, by the way? It tells you that all four angles are right angles. Exactly. So this is a right angle, this is a right angle, this is a right angle, and this is a right angle. Okay. And so we also know that DCE is equal to FBA. DCE, that's this, is equal to FBA, which is this. I'm going to use those as to indicate that the two things are equal. Prove that ABCD is a parallelogram. By the way, how do you prove that something is a parallelogram? There are a whole bunch of different ways to do it, but give me an example of how you would prove that something is a parallelogram. You can prove opposite sides are equal. Good. You can prove that opposite sides are parallel. That's good also. You can prove that opposite angles are equal. Both sets of opposite sides are equal. Both sets of opposite angles are equal. Both sets of opposite sides are parallel. You can also prove that diagonals bisect each other. There are a whole bunch of different ways you can prove a parallelogram. But let's first start by writing what we are established in terms of the statements and the reasons. Well, let's first start with what we're given. Let's say AFDE is a rectangle. I'll abbreviate it here, and we'll say that angle DCE is congruent or equal to angle FBA. And those, for both of them, we'll say given. Okay. Now, let's look at this and see if we can come up with a strategy. Well, let's say this is equal to this. I'll make 2 ticks over here and 2 ticks over there. Okay, let's look at this and come up with some sort of a strategy for how we're going to go about doing this. Anybody have an idea in terms of what might work for a strategy here? Okay. Well, what does it look like right away we can do with those triangles? Okay, we can show A, B, and C, A, B, and CD equal. That would definitely help, of course. Absolutely. How do you think we might go about doing that, though? You know what I'm going to do? I'm gonna put this on hold for a minute. I'm going to put this on hold, and I want to go through the next few slides. 1 second. Let's freeze this here. Let's freeze this here and come back to it a little bit later on, because I think let's go and look at how we would prove various things. Okay, actually, you know what? I don't even have to go through it because I actually did it on the next slide. Okay. Well, it says this is what we have so far. This is what we have so far. Okay, we have opposite sides. We have this angle being equal to this angle. That's what we were given. We were also given opposite this angle. The corner angles are equal. Okay. Now, can you get any other information? Let me get rid of this. Now, because this is a rectangle, because we were given that the entire thing is a rectangle, the first thing that I can see right away is that because it's a rectangle, I can get this side is parallel to this side. Remember, because in a rectangle, just like any other parallelogram, opposite sides sets of opposite sides are parallel. Once we have this, once we have these two sides, for example, that these are parallel, well, how about these angles down here? And there are probably many different ways to do this. How about this angle? Let me use a different color here. How about this angle down here? What is that equal to? Anybody remember what those things are called? This angle is actually equal to this angle. These two angles are equal to each other. See why that is? Anybody remember the alternate interiors rule? When we discussed parallel lines? Well, okay, you know what? Let me go through this, and I'll just establish this proof, and then we'll kind of go through how we do the proofs in general, and then later on we'll do one together. So first of all, we can establish that this angle, this angle and this angle are equal to each other. And the reason is because there's a general rule that when two lines are parallel, angles that are on opposite side of whatever cuts them are equal. So for example, I could say that angle BAC is equal to, or con to, let's say, angle FBA, because they are alternate interior angles. Again, that is a general rule to all parallel lines. When you have two parallel lines and they're cut by a third line, angles that are on opposite sides of that line are equal. And of course, the same thing is true to between this and this. They're also alternate interior angles. So I'll also say angle DCE is congruent to angle CDB. Again, we're about this one and this one. And for the same reason, same as the previous one. Now, based on that, we can establish that this angle is equal to this angle. Do you see why that is? We knew from before that angle FBA, let me number them in order to make it a little bit easier to remember. I'm going to number them. I'm going to put this as angle 1, and this is angle 2, and this is angle 3, and this is angle 4. We already were told before that angle 1 equals angle 4. That was one of our givens. Well, we know that angle 1 equals angle 2, and angle 3 equals angle 4. That tells us by definition that angle 2 equals angle 3, because they're both equal to angles that are equal to each other. That's also sometimes known as the chain rule. If A is equal to B, and B is equal to C, well then C is equal to A. Common sense, right? So let's say over here that angle, we could name them, but for our purposes, let's just use them as numbers. That's fine. Angle 2 equals angle 3 because they angles that equal each other. Okay, what else can we do? Well, can we do the same thing? Let's say for example we made this angle 5 and this angle 6. Could we do something similar for angle 5 and angle 6? Well, let me ask you something. What's the relationship between angle 5 and angle 1? Right, 1 and 5 are supplementary. Why? Because they are on the same line. They're an ordered pair on the same line. They're a linear pair. So I'll say over here that angle 1 and angle 5 are supplementary. We also say for the same reason that, let's say, angle 4 and angle 6 are supplementary. Okay. And I'll for the reason I'll say, okay, I'll just say sorry. A linear pair. A linear pair means two angles in the same line of angles are, and I'll use diagram to mean angles. A linear pair of angles are supplementary. On that, what's the next logical step? If angles 1 and 5, if angle 5 and 1 are supplementary, and 4 and 6 are supplementary, and 4 and 1 are equal. Okay, so can I then say angle 5 congruent, which is again same thing as equal, essentially, to angle 6? And the reason why I can say that is because each angle is supplementary to angles are equal. Sorry if I'm running out of room down here. So now what do we have? Now we've got angle 5 equals angle 6, and we've got angle 3 equals angle 2. Now can we prove what we're looking for? Can we prove that ABCD or ABDC is a parallelogram? The answer to that is yes. We can say that ABDC is, I'll just abbreviate here, and the reason is because opposite angles are equal. Now, if I had a bigger piece of paper and a little bit more time, I'd write it out a little bit more formally. Like, instead of just saying opposite angles are equal, I would say in a parallelogram, opposite angles are equal. But all I really did in this case is I just, took the whole thing that we had and figured out, okay, what can we start proving by what we're given? And once we start proving things by what we're given, you'd be surprised how easily these things tend to fall into place. And was that the only way we could have done this? The answer is no. There were other ways we could have proven this thing. We probably could have proved AFB is congruent to the triangle CDE, and then we could have proven the side because they were similar sides. There were other ways we could have done this, but that was certainly one way to do it. It was a relatively simple way to do it. Okay, now again, I'm not expecting you to be able to do this right away. I just wanted to kind of illustrate how they work. Because what we're going to be doing for today is we're going to be proving triangles. And proving triangle congruence requires that now congruence, remember, means that the two shapes are exactly the same. That if you took one and put it on top of the other, they would fit precisely. That's what congruence means. If I want to establish that two triangles are congruent, there are really a few possible ways to do it. Again, if I want to establish that triangle, let's say ABC, and triangle DEF are congruent, there are really three ways that I can do it. Number one, I can prove it by side angle side. SAS is congruent to SAS. That means if I can prove that two corresponding sides are equal to each other, and then I can show that the angle in between them is equal, then I know the two triangles are congruent. So if I can prove AB is equal to DE, and then I can prove that BC is equal to EF, and then I can do the angle in between, angle E is equal to angle B, I have now proven that these two triangles are congruent to each other by a method called SAS, because they're side, angle, side. Now, by the way, if you think about why that is, once you have a side and an angle, there's really only one way you could finish this triangle. If I have two pieces, imagine two pieces like this, where imagine these two shapes are precisely the same. Same angle, same length. There's only one way this one could be finished, and that's with this line, and that's the same way that this can be finished with this line. So, side, angle, side. As long as you can prove the two triangles have a common and equal side, and then another side, and the angle in between, that's enough. Not ASS, no pun intended over there. So in other words, the angle has to be in between the two sides. So for example, if I could prove that this is equal to this, and this is equal to this, and this is equal to this, have I proven that these two triangles are congruent? No, I haven't proven it. Oh, actually, you're right. I have. I'm sorry. My bad. My mistake. Yes, you are correct. That's in fact our second method. But what I was trying to get at was, let's say I have two triangles like this, So you're correct about that. Let's say I have two triangles like this, and I prove that this side is equal to this side is equal to this side, and this angle is equal to this angle. Have I proven that the two green triangles are congruent to each other? The answer is no, not yet, because I've only proven side angle. I haven't proven side angle side. Okay. The one in the upper right-hand corner, on the other hand, as we discussed, these are equal because this is a proof method known as ASA. Or, really, actually, this is angle side. I'm sorry. Well, yeah, you're right. Okay, this one is really AAS is congruent to AAS. Angle side is congruent to angle side. And the point is, all you need is any one side and any two angles. So this applies whether the side's in the middle or whether the side's not in the middle. It doesn't really matter. Really, two angles plus one side is all you need. If you can prove two angles and one side, you have now proven that the two triangles are congruent. The third possibility is if this, of course, does not work. The third possibility is if you prove that all three sides are equal. You prove this side equals this side equals this side, and this side equals this side. This is SSS is congruent to SSS. And the fourth possibility is specific to a right triangle only. If this is a right triangle, and this is a right triangle, so the right triangle works the hypotenuse plus a leg, either leg, is congruent to the hypotenuse plus either leg. So in other words, if this is equal to this, and this is equal to this, we have now proven that these two are equal. Now this is really ASS or SSA, so even normally, just two sides and an angle that's not in between them, I said before, does not work. But it does work if it's a right triangle. If it's a right triangle, it's a specific special rule that if it's a right triangle, the hypotenuse plus one of the legs is sufficient to prove congruence. Those are really the four ways to establish triangle congruence. Okay. Yeah, well, again, just want to make sure that I think that's a good way to remember that it doesn't work. Okay. That's our four ways that we can prove triangle congruence, and we're going to look at some examples over here. Before we look at the examples, there are a few very common rules. During the course of what we've discussed so far, we've learned a lot of rules in geometry. We're going to learn a lot more rules in geometry with regard to quadrilaterals, with regard to triangles, etc., but there are some things that are going to come up over and over again. These are either postulates or theorems. These are, again, just different mathematical rules, and they're all relatively simple, but it does make sense to go and discuss them a little bit. Once you have the first rule is the corresponding parts rule. The corresponding parts rule says that if you have two triangles that are congruent, and this applies to quadrilaterals as well, but if you have two triangles that are congruent, well, you can now say that all of the corresponding parts are equal to each other. Let's say we proved that this was equal to this angle was equal to this angle, and this side was equal to this side. First of all, have we proven that these two triangles are congruent to each other? Just by virtue of what we've discussed so far? Yes, we have, because we've gotten it by side angle side, right? Now, based on this, we can now also prove by the corresponding parts rule that this side is equal to this side, that this angle is equal to this angle, and that this angle is equal to this angle. In other words, once you establish congruence, everything else falls into play. All the corresponding parts of congruent triangles are equal. Number 2 is one of the most obvious mathematical rules you were ever going to see in your life, and that is the reflexive property. Anybody know what the reflexive property means? This is going to blow your mind in terms of how intelligent and profound it is. Well, it's even simpler than that. Reflexive property is that something is equal to itself. Exactly. So if I have, for example, a line, let's say, and this is point A and this is point B, well then AB is equal to, or congruent to, AB. Well, that seems pretty obvious, right? Now you might say, well, Stephen, isn't that, why do we need to know that? What does it have to do with anything? Well, the answer is, let's say, for example, we've got something like this, and we want to prove these two triangles congruent. Triangle A and triangle B. We want to prove these two triangles congruent. And let's say we can establish that this angle is equal to this angle, and we can establish that this side is equal to that side. Well, now we could simply prove that the two triangles are congruent by establishing that this side is equal to itself, and now we've got SAS. Now we've got side, angle, side. So the reflexive property is extremely simple, but it's also the sort of thing that you're going to use. The bisector property is simply that a bisector splits something into two. If I tell you, for example, that CD is a bisector of AB, that means it splits AB in half. That means this side of AB is equal to that side of AB. Supplementary and complementary angle rules, we've discussed this earlier in the course. Hopefully you all remember. Supplementary means when two angles equal 180 altogether. So if this is 70, how much is the other angle? I'll get to the perpendicular in a minute. Okay, that's 110. That's right, because they're supplementary. Complementary is if there is a right angle, a 90-degree angle, then the two, let's say this is 30, then how much is the other angle over here? 60. Okay. The perpendicular line rule says that if two lines are perpendicular to each other, that means they form at a right angle. This line is perpendicular to this line. Let's say, for example, this is A, and this is B, and this is C, and this is D. So the way I would write it is AB is perpendicular. If that's true, then it forms at a right angle. By the way, so how many degrees is this angle over here? The one that I just put in. 90. How about the one next to it over here? Also 90. And this one's 90, and that one's 90. In fact, if you have perpendicular lines, you don't just have one right angle, you got four right angles, by definition. Number one, because they are supplementary with the ones next to each other, and also because they're equal with the ones opposite because of the vertical angle property. Remember, you have, let's say, if you have, angle 1, angle 2, angle 3, and angle 4, so angle 1 equals angle 2, and angle 3 equals angle 4. Because they are vertical angles. They're on opposite sides of the line. And finally, you've got the exterior angle rule. The exterior angle rule says in a triangle, if you, let's say, extend a triangle, and let's say this is angle 1, and this is angle 2, and this is angle 3, and this is angle 4, the exterior angle rule says that angle 4 equals angle 1 plus angle 2. The exterior angle of a triangle always equals the opposite two combined. And if you think about it logically, that makes a lot of sense. What do 3 and 4 have to add up to altogether? 180. Why? Because they're a linear pair. What do 1, 2, and 3 have to add up to? Also 180. Why? Because the three angles in a triangle have to equal up to 180 degrees. Well, now if 3 plus 4 has to equal 180, and 1 plus 2 plus 3 has to equal 180, well, pull 3 out, which is obviously equal to itself. 1 and 2 combined have to equal 4. So the exterior angle rule, exactly. 1 plus 2 has to equal 4. That's the exterior angle rule. Okay. With that in mind, let us do some proofs. Okay. One second. I'm having a little trouble with this. Give me 1 second here. I'm sorry. I know, if you're typing, I unfortunately can't see what you're typing because I'm having a little trouble with my monitor, but we'll get it fixed. Okay. Okay, I'm having a little trouble with my monitor. You know, I'm gonna have to come back into the classroom in a second. For some reason, I'm having a little trouble with my monitor. Sorry about that. Can you hear me okay now? Yeah, okay, but the thing is, you know, for some reason I'm having trouble. Anyway, what can you see now? Can you see my paint, or can you see can you just see a blank monitor with my browser over here? Okay, you can see the paint. Okay, fine. There's something bizarre about this new Connect that's confusing me a little bit. But all right, what are you gonna do? We'll do it like this. This is not the way it's supposed to look to me, anyway. But you probably have absolutely no idea what I'm talking about. So, all right. Okay, fine. So we've got it. We've got a kind of a shape over here. We've got a quadrilateral over here, and we've got, given that BC is congruent to CD, which are these two lines over here, AC bisects BCD. Prove that triangle ABC is congruent to triangle ADC. Okay. So how are we going to go about proving this? This is a relatively simple one, but let's make our chart. Okay. What should we put first as our first couple of statements? Well, let's use our givens. Okay. So let's put in BC is congruent to CD, given. And then we'll say AC. Okay, so and we'll say AC bisects BCD, also because it's given. Okay. Anybody have an idea of what we should do next once we've established these two givens? Okay. So the developer says the first thing we can do is get these two angles. Get angle 1 and angle 2. And you can do this, by the way. You can actually call them 1 and 2, or you can call them by their full formal names, which is angle BCA is congruent or equal to angle ACD. Why is that? Because of the bisector rule. A bisector forms two equal angles. Okay. So what do we have so far? So far we've got a side and we've got an angle. How do we get the third side? What third side can we get? Well, how about AC is equal to AC? That's right. Remember we just discussed this a couple of minutes ago? AC is congruent to AC. And anybody remember what that was called? Okay. That was called the reflexive property. By the way, I think I see what was confusing me before. Actually, it's an improvement on the Adobe screen sharing, but unfortunately it confused me a little bit. But okay, so yeah, we've got the reflexive property. Now, what do we have? Exactly, now we've got a side, which was BC and CD, that was given. We've got the angles in the middle, and we've got the sides in the middle. So we can now say that triangle ABC is congruent to triangle ADC because side angle side is congruent to side angle side. Okay, well, that was a relatively simple one, right? Let's do one. Let's try another. Let us try another. 1 second, I had this. Okay. For the homework, let's save the homework for class. We're going to be doing a bunch of these, so let's save the homework for class 6. Some of the homework ones, but let's do a couple of other ones. I want to do some simpler ones. The homework ones are generally speaking a little bit more difficult. Okay. So let's put down here. Statements. Okay. Okay, let's say statements. And we'll put reasons here. All right, so what do we got over here? We have two triangles here. We've got given that AB is equal to ED. We've got C is the midpoint of BD. And we've got AB is perpendicular to BD, and that ED is perpendicular to BD as well. Okay, and prove that the two triangles are congruent. So let's establish all of these to start with. And you know what? Rather than type them over, I'm going to copy this, put it over here, and I'll just do it to all of them. All right, you can. I'm sure you can see it. We'll just put. Yeah, this is actually a very easy one as well. Given. Okay. Well, what should we do? We've got a side. Now we need an angle and a side, or two sides, or two angles. Any of these things. Okay. How about can we get this as a right angle? Sure. We can say angle B is a right angle. How do you know it's a right angle? Because AB is perpendicular to BD, and perpendicular lines, I'll use that symbol for perpendicular. This is the symbol for perpendicular, as you see over there. Perpendicular lines form right angles. Okay. And we'll say angle D is a right angle for the same reason. So we've got these two are equal. Now, what next? So we've got angle D and B are right angles. Okay, we've got BC is, let's say, congruent to CD. Why is that? This is the bisector, or the midpoint rule. A midpoint divides a segment equally. Okay, are we ready yet to prove it? Not quite. I mean, so we've got, let's say, this side to this side. Well, we don't quite have SAS yet. I mean, we've got one more small little link left. We know that B and D are both right angles. Does that mean they're equal to each other? The answer, yes, it does mean that, but we have to say that. We'll say, let's say angle B is congruent to angle D because all right angles are equal. I know it may seem obvious that if they're both right angles, they're equal to each other, but we still have to say it. It's still part of the proving process, is establishing that they're equal. Now that we have angle B is equal to angle D, now we've got the triangles. Now we've got triangle ABC congruent to triangle EDC, and it's all based on side angle side is congruent to side angle side. Okay, I want to do one more before, and let's try to find one that's a little bit more difficult. Okay, how about this one? This one looks better. Okay. One second now. Okay. Let's put this over here. We'll do the proof on the right side this time. Okay, this one looks a little bit more difficult. No? Okay. We've got angle A equals angle E. And by the way, I haven't touched these, so honestly I have no idea how to do them to start with, but let's figure them out together. Angle A equals angle E. AB is congruent to BE. So that's this whole side and this whole side. Prove AD is equal to EC. So they want this side and this side. Well, how do we go about doing this? Okay. Okay, but what are we gonna? I'm thinking this right now over here. We've got an angle, and we've got a side of two triangles that are kind of overlapping here. Right? Think about these two triangles. Just looking at this, this is one that you'd probably have to think about for a little while. What about these two triangles? Imagine these two, this triangle, which is triangle ABC, and then imagine this triangle, which is triangle DBE. These are overlapping triangles, and I think this is what Devorah was talking about over here. But if we talk about these two triangles, you know, in order to keep them, let's outline this. Let's put this in red. Whoops. And this in blue. And put this in purple here in the middle. I'm putting it in purple because it's a combination of red and blue. Imagine, so if we're thinking about these two triangles, we really have an angle of each one. Angle A and angle E is an angle of each one. We've got a side of each one, because BE and AB. And then we've got angle B is equal to itself based on the reflexive. So how about that? And once we do that, yeah, then we can start messing around with corresponding parts. That's what I'm thinking about in terms of a strategy. There may be a shorter way to do it, by the way. But okay, so let's. But the thing is, okay, so how is that? But let's see. But once we get those two triangles, so how is that going to help us get AD, which is this side, this segment, and CE, which is or EC, which is this segment? There's like a little riddle over here almost. Once we've got the two sides, well, we already have the angles anyway, so that we don't really need. We can get, oh, okay. Then we can get let's put in another letter here. Let's put in the letter F over here at this point here. Now, can we get a triangle ADF and FCE? If we get those two triangles, then we can get CE and AD based on corresponding parts. Well, there may be other ways to do it, but once we do that, then we can get the two sides on corresponding parts. That's what I'm thinking of. So then again, there may be other strategies. There may be 10 different ways to solve this thing, but that's the thing that I'm looking at right now. So let's do the whole thing here. Let's start with the statements, and then we'll put the reasons here. Okay. Okay. So first of all, let's put in what we have. Angle A is congruent to angle E because it's given. Then we've got AB is congruent to BE, also given. Okay, simple enough. Now, we discussed also looking at we have this angle over here and this angle over here, and then we've got the two sides over here. And then the third thing we decided was to get this angle here. Let me use a different color as this is not, you can't really see it. Then we decided to get this angle. So we'll say angle B is equal to angle B, and we'll base that on the reflexive. So now we've got angle, side, angle. We've got this angle and this angle, this side and this side, and then angle B over here, which is these two big triangles. So now we can get triangle ABC is congruent to triangle DEB. Again, this whole thing and this whole thing. And this we did based on angle, side, angle. Okay. Now I'm breaking it down to these smaller triangles. The smaller triangles, I'm doing ADF is congruent to triangle, not angle, triangle FCE. And for here, see here what I'm saying is not necessarily going to, well, I mean this is the second to last step, so I don't think it's necessarily any harder. But okay, but so over here, what I'm gonna have to say it in in plain language here. I'm gonna say. Subtracting the same quantity from each congruent triangle. In other words, all I really did is I subtracted the purple stuff. I subtracted the purple from this whole thing over here and this whole thing over here, leaving these two. And whenever you take two things that are equal and subtract the same quantity from each, the result, of course, has to be equal. And so once we have that, now that we've got these two triangles, we can now get what we're looking for. We can now get AD is congruent to CE, and this is based on corresponding parts. Because this and this are corresponding parts of congruent triangles. Okay, Dvora, what was your way? You wanted BA minus BD. BA minus BD and BE minus BC. But how did you know that BD is equal to BC? But corresponding parts doesn't give you BD and BC. Corresponding parts gives you AB and BE. Remember, if you haven't proven the smaller triangles, so I don't see what gives you this and this. The whole sides it gives you, but let's say this and this, I don't see how those wouldn't be corresponding parts of the entire triangle. Those would just be, you're talking about from here to here and from here to here. Oh, I see what you're saying. Okay, in other words, okay, BD is the base of BED, and AC is the base of ABC. Okay, I see what you're saying. Okay, so that you could get those two on corresponding parts, right? Because this is the base of this whole triangle, and this is the base of this whole triangle. And so therefore they're corresponding parts, and once you have that, then you subtract. Okay, I mean, again, same number of steps, so I don't necessarily know that one is any shorter than the other, but okay. But yeah, that would be a good alternative strategy. Okay, so again, this was a slightly more complex proof. Next time we're going to, again, I know this is fairly complex. I imagine some of you may be a little mystified, but that's okay, because really we're going to spend an entire class next time going through these proofs. And I'd really like you to ask questions if you have them. If you're not, don't be embarrassed if you're not sure how we did something. Next time, we'll do 5 of these or whatever it is, and I'd really appreciate it if everybody would chime in with questions if you want me to re-explain a particular step. And by the end of next class, hopefully we'll be able to be very proficient at these types of proofs. So, thank you so much, everybody, for coming. If you have any questions, please feel free to stick around. And have a fantastic evening, everybody.